Welcome to the podcast of FENS Virtual Forum 2020. We'll be looking at the highlights of Day 3, Monday the 13th of July, and catching up with the people behind events. First up, we spoke to Dr. Dervila Glynn, Chair of the FENS Communication Committee, to spotlight the special interest event using Twitter to communicate in your science life.
Well, the Twitter event is actually really exciting. We're actually holding a panel discussion here at the FENS Forum. We've got a really esteemed panel. We have Professor John Cryan from Cork. He's a professor of anatomy and neuroscience. We have Helena Ledmeyer from the INCF, who's the Director of Communications there. We have Anne Cook, who's the Chief Executive of our host society, the British Neuroscience Association. And we have Mo Costandi, who's a freelance science writer. So we have really four completely different angles, and we want to talk to these and get their insights into how they communicate using Twitter and how they use it as a tool. What are the advantages, disadvantages, any pitfalls, any tips that they can give us, and really kind of promote the use of Twitter and rather than kind of seeing it as a gimmick, that kind of takes up your time as in academia, but what can it actually give you? We've also created a how-to guide for FENS and Twitter. So if you're new to Twitter and you want some guidance and some tips, you can just follow this quick and easy guide to get you started.
Dr. Dervila Glynn also gave us some background to this year's forum.
I work very closely with the FENS team in Brussels. So Lars as the chief executive and of course Louise as the head of communications there. So I've been really lucky to work alongside them. We also have a communication committee, which are voted members from across Europe, which have been, we've really worked together, and we've put a load of initiatives together for this forum. So things like the social media ambassador program, which has been really quite different. We have 18 researchers from across the world involved in tweeting, blogging, kind of really posting their own experience from the FENS Virtual Forum. And then we also have had a first for FENS this year, and what we have are these voluntary press office and communication assistants who, it has been really exciting. It was an opportunity to provide some kind of professional development opportunities. And we have 3 voluntary press office and communications assistants, Harry, Anders, and Shruti, and they are doing a wide variety of tasks. So they're helping in the press office, they're helping with these podcasts, they're helping with the social media aspects, they're helping with all things communication at the forum. So that's been really exciting. I've been very fortunate to have a really good team, and of course the rest of the executive committee at FENS and the program committee for the forum. I've been really fortunate to work with such a team. Working with FENS, it's a real wide community, and I would recommend anyone to kind of take the opportunity if they get a chance in the future.
I've always been fascinated by behaviour, and I've always been fascinated by how the brain controlled behaviour.
Our next highlight is the Behavioural Brain Research Lecture on prefrontal circuits related to anhedonia and anxiety, delivered by Professor Angela Roberts.
And when I talk about behaviour, I mean, human behaviour, social interactions, how we regulate our emotions, how we think. And it's always been fascinating to me how the brain can actually do that. So that's my original interest. But then, of course, I very early on began to appreciate what happens when, you don't regulate your emotions very effectively. And then I, saw the path that actually I'd really like to be able to study something that could actually help us understand human behavior more, so that it could actually help people who have problems with regulating behavior in one form or another. So I think that's really how I got into it. We're trying to find out exactly what the role of the different changes you see in the brains of patients with depression, how causal they are to the actual symptoms they're experiencing. So we know from human neuroimaging studies that there have been, for example, increases in activity in a particular ventral part of the prefrontal cortex, which we know is particularly important for regulating emotions. And that increased activity has been seen, but it varies between studies as to exactly where it is. Sometimes it's more in the back part, sometimes it's more in the front part. It's a difficult area to image. There are problems imaging that area of the brain with the scanner. There's lots of artifacts that make it difficult to really locate where the activity is. And this is and we're talking a large area of ventral parts of these frontal lobes. And so whilst it seems like there is increased activity, and importantly, when patients are treated successfully and so they lose their symptoms, the activity seems to go down. So it looks like that might be quite an important area for causing depression and for trying to effectively treat it. But again, because it's correlatory, what we've started to try and do in our animal studies is to focus in on that area and be able to make very localized manipulations and look at the effects specifically on these types of symptoms, these different kinds of anhedonia, and also anxiety, because very often patients who have depression usually often have anxiety issues as well. And so we're starting to be able to properly determine whether changes in the activity of a specific region can actually cause specific anhedonic symptoms. So what we're hoping to do with the research is, once we've potentially found an area of the brain which, when we manipulate, produces a symptom very similar to what we see in patients, and that area in the brain we know in patients shows that change, so it's all tied in together, we can then try out specific drugs and see which ones ameliorate and which ones don't. And then we can start building a picture of where are these drugs acting in the brain to have their effect. And then if we know that, we can go back to the patients and see if we can work out, so which patients are most likely to be sensitive and be treated effectively by one particular drug class versus another particular drug class. So that's the overall aim.
Professor Andreas Meyer-Lindenberg delivered the presidential lecture on neural mechanisms of environmental risk for psychiatric disorders.
The evidence base for cities being bad for mental health is overwhelming, surprising really, because cities are good for pretty much everything else. Cities are good for education, for economic activity. They bring people together. City dwellers are also often somatically healthier. They tend to be less overweight, etc., etc. So the brain and mental health is the one outlier, but it is a stark outlier, and says that we pay a price for city living. And as more and more people are urbanizing, which is a process that's probably unstoppable, right? It's already proceeding very rapidly, driven mainly by Asia, for the positive aspects that cities have, and it's accelerating, for example, through climate change, because climate change involves displacing, for example, the majority of people who live near the coast. They have to move somewhere, and they're going to move to big cities. So that's unavoidable. And I think the impact on mental health is going to be bad, right? So this is going to worsen our mental health. And the question really is, how can we mitigate this? I don't think we can make that somehow not happen. It's also quite unreasonable to think that maybe somehow everyone could return living in rural circumstances, because there are just too many people in the world for that to be feasible. And there's the additional pressure of needing to have a sustainable climate impact. So the cities of the future are not going to be a house with a garden and a house with a garden. The cities of the future are going to be very dense. And we know that that's a bad thing for mental health too, living in high rises, having no access to nature and so on. All these things are additional factors that are deleterious. So actually one of our main research foci is trying to bring neuroscience to the conversation and ask, what aspects of the city can we make more amenable to mental health? What can we change, given that we will have to work and live in dense cities? What can we change to make them less bad? But I don't think there's a scenario in which this will be good. The question of using apps in therapy, clearly that's a yes. This is already being done. And we know that patients like this approach, that it's in the studies that have been done, non-inferior. So it's as good as doing it face-to-face in many of the things that have been looked at. So I'm certain that the use of apps will increase in psychiatry, and we have unique chance in psychiatry because we can actually treat, we can, send interventions through an app, and that's a unique ability that we have in psychiatry. So that's a definite yes. The approach that we've shown to look at the environment, so the context in which someone is through sensors and things like geolocation, figuring out where you are on a map, does that impact the clinic? I think the answer here will also be yes, because bringing in the context is a very powerful modifier of how someone feels with a mental illness that we didn't really know about until we did that kind of research. We now know that really your context is hugely important, and whether or not you hear voices, or the fact of whether or not you move is important for your mood. Or, for example, we have a research project going on right now in Germany where we're looking at people who drink a lot but aren't at the threshold for addiction yet. What happens if they drink so much that they're about to fall over the threshold? That's something that you can unobtrusively monitor with the patient's consent, of course, using a phone. And once they do, then you can intervene, right, and say, hey, what's going on there? Want to talk to a therapist? Here's some tools that you can use. So that's also yes. Thirdly, the neuroscience aspect of this. We are seeing what happens in the brain of someone who's being exposed to, for example, city living, and how is this changed if those people experience a lot of nature. That is primarily research, but however, it drives an understanding of clinically useful prevention and intervention programs. For example, we talk about a recent paper we had in Nature Neuroscience, where we are asking who profits the most from green space in cities. And what we found is that those people profit the most are the ones that cannot regulate their emotions intrinsically by prefrontal activation. And an at-risk group who benefit from green space, because green space basically calms them down or regulates their emotions for them. Now, that is a neuroscience finding, but it can guide an intervention, because we can characterize this population and then make sure they have equitable access to green space, for example.
Next up is the Max Cowan special lecture entitled Synapses Lost and Found, Developmental Critical Periods and Alzheimer's Disease. This was delivered by Professor Carla Shatz, who tackled the thorny issue of pruning.
I was just outside in my garden pruning, and pruning is it is removal, but it's the selective removal of branches along a main arbor. So it's really about removing parts of a whole, leaving the rest, perhaps even to thrive. And it's, I make that distinction because it's different from synapse loss or elimination, in the sense that that's a more broader term. You don't really know in synapse elimination or loss. All you know is if you count synapses, there are less of them later, let's say. That's loss, no question about it. Now, why does that happen? Does it happen because of the death of the whole neuron? So all of the branches and connections go, or does it happen because there's a selective removal, which you can call pruning, which I would call pruning. And synapse pruning is something that happens during development. And I think this happened, for my lab, studying this and discovering this really happened many, many years ago. And it happened at about the time that people were also studying synapse loss and elimination in other parts of the brain, Peter Huttenlocher, by counting synapses. So in development, the pruning that happens, for example, in the visual system, in the retinogeniculate pathway, which is what I talk about in the lecture, that pruning is highly organized and specific. And the remodeling that happens gives rise to an adult pattern of circuit connectivity. So it's highly directed. It's that kind of pruning that we think is disturbed and altered in disease states. And it's what really made us look at Alzheimer's disease. Again, because people talk about synapse loss and neuron loss, but very little work has actually been done to distinguish between wholesale loss of synaptic connections versus a kind of unregulated pruning that might happen in disease. And I actually think, you could say, well, who cares? I mean, if you lose it, you lose it. This is, dreadful because if your memories are stored at synapses, you lose a synapse, you're toast. But I think we should all care and make the distinction, because mechanistically, these could be driven by different signaling pathways and different mechanisms. And I think, if you really want to understand both developmental mechanisms of how circuits get formed and tuned and early on, and also mechanisms of neurodegeneration later in life, the distinction should be, one should be aware of the distinction. Very nice. They wrote back to the editor and told the editor that they respected me as a scientist, but I must have done something terribly wrong, and I should go back to the lab and figure out what we did wrong. Now, this was, I think, pretty upsetting to the postdocs in my lab at the time, but so they had helped me, now I'm going to help them. So I basically said, well, we have two choices here. We can go home and cry and give up, or we can get really pissed off and angry, and we can show people that, they're wrong. And I mean, that's in a way what good science is about. But I think you have to have the inner fortitude, and it doesn't hurt to have tenure. Well, it always looks like, you have this great career, you never have any problem, you're always publishing in good journals, but you have no idea about the fights that have gone on, because frankly, we almost never discuss them because we don't want to discourage everyone. But for every really big discovery that my lab has made, we fought for it. The fun thing about science is to actually discover something that nobody's seen before, but it's also terrifying. And I think you do need to have a support network that you've built over the years.
Also today, Professor Johannes Gräff delivered the Berenke Ingelheim FENS Research Award lecture.
So epigenetics is the study by which the activity of genes can be regulated. So we have the level of the genes, which are the same for all the cell types in our bodies, and yet our cell types are not the same. So a neuron is not a skin cell, as you know, and as everybody experiences. And what makes them different is this additional layer of regulation that is the epigenetic one. And so they can be installed by the environment through development, for instance, or by changing environments. And at the same time, they can be extremely stable. So a neuron will always remember being a neuron throughout the lifetime. And that is because of those stable epigenetic modifications. I mean, the link to cognition or learning and memory is that learning and memory also depend on a particular set of genes being properly controlled. And if that's no longer the case, then we can have learning and memory impairments or even neurodegeneration. And over the past 10, 15 years or so, there's more and more evidence surfacing that these epigenetic modifications do participate in this regulation of gene expression in learning and memory. And when they're misregulated, well, then we have cognitive impairments. We have to start somewhere. So for instance, you know that Eric Kandel won the Nobel Prize on his work on aplysia. And aplysia is a simple marine mollusk. And the beauty of this Nobel Prize is that he can break it down to essentially one giant neuron and study this, or several neurons. And I think we have to start somewhere. So the field of epigenetics is very similar, and I would also say the field of epigenetics in brain research is still at the very beginning. So we will pick a few marks, histone marks, DNA methylation, and then just start to study them. And already by doing this, we could gain a lot of insight into, how they are implicated in normal learning and memory, in healthy learning and memory, but also in unhealthy learning and memory. And so I would say it's a platform for, tackle this almost infinite complexity of epigenetic mechanisms that will come afterwards. Some papers have looked at multiple epigenetic modifications, and it turns out that only a few of them are always the ones that are regulated. So maybe out of all these combinatorial possibilities, it's really only a few that we have to understand that might serve as master regulators, but this we don't know yet. Following up on our own discovery and that of many others, so it's known that several conditions that are characterized by cognitive impairment have a decrease in histone acetylation. And this decrease in histone acetylation is mediated by these enzymes called histone deacetylases, so HDACs. Now, luckily for us, they are amenable to pharmacological manipulations, to small molecules that inhibit the activity of these enzymes. And so various studies have used them in a preclinical setting, that is in rodents and also in fruit flies, by the way. And they could show that if we treat animals with these HDAC inhibitors, not only could the histone acetylation be reversed, but also to some extent the cognitive impairment could be reverted. And that's very promising going forward, obviously, to treat people with cognitive impairment, also with these HDAC inhibitors. And so currently there are 2 or 3 clinical trials going on that are looking at this, and we're eagerly waiting for the results. I can see two big challenges in the field. One is the transition from the preclinical phase to the clinical phase, which is a challenge everywhere, and also for these HDAC inhibitors or for any type of epigenetic drugs. And then the second challenge is to really tackle the complexity of the brain in terms of cell type heterogeneity. So far, the field of epigenetics in learning and memory, we've been looking at a few cellular subtypes. And yes, we understand how epigenetic modifications work in there, or we start to understand that. But how is this in a cell that's maybe not implicated in memory? Or how is it in astrocytes? How is it in interneurons? This is really not known yet. And so there's a lot of room to explore, and it's very exciting, but at the same time, it's also a big challenge for sure.
Finally, we go back to a guest you heard on yesterday's program.
In science, where we're chasing after the unknown. And so while we all think, science thinks it has good ideas about how to understand the unknown, we don't have all the approaches and we don't have all the ideas. And if we just make use of half of the smart people in the world to think about the problem, we're not going to get there, right? So I think it's pretty logical that we need to make use of all the different minds we have.
We congratulated Professor Erin Schuman on being the winner of the ALBA-FKNE Prize for Diversity.
I speak up a lot on committees and on advisory boards and grant panels for the representation of women and for the fairness of the process. At my own institute, together with my colleagues, we fought very hard to have childcare, to put a childcare facility on campus. And actually we have an infant childcare room in our institute that we built, that we kind of retro fashioned when we discovered that the local childcare people are not interested in taking care of babies before they're essentially 1 year of age, which is death for most scientists, I would say. In my society, in the Max Planck Society, when I first arrived 10 years ago, scientists are clustered in institutes, and those institutes are run by directors. And in the section that my group is in the biomedical section of the Max Planck Society, there were only 10% women at the director level, which in 2010 was very, very low. Even if you look at other institutions that pride themselves on excellence, 10% women at the highest level was a very low number. And together with colleagues, we worked on writing an initiative and changing the recruiting practices. It was called 20 by 2020. And we got that passed by all of our colleagues and worked hard in the next 10 years and made it to around 18% female directors. So that's something that I'm very proud of, and I suppose was also recognized in giving this award. Yeah. Now it's probably too early to say, but we've recently in our section passed another initiative, again with a new target. So we'd like to get to 30% by 2030. With the slightly different mechanisms, taking a look at institutes that actually don't have any women, have 0 female directors, and really working hard to make sure that we can recruit women at those places. And I'm optimistic. If I compare the amount of enthusiasm and the general sort of traction that these ideas get, was a lot easier this time. A lot more people are on board and a lot more people are enthusiastic about these things.
That's it for this time. Join us again tomorrow for Tuesday's highlights from the FENS Virtual Forum 2020. This podcast was made with the support of the Dana Foundation.